Okay, so welcome back to another lecture. We have been talking about moment of inertia. So this class we will be talking and concluding the discussion on moment of inertia, and then we will move to the 3D dynamics or 3D three-dimensional kinetics. So that's the objective. Last class we we looked at the basic concept of your moment of inertia. It was defined as integral of like y square dA was ix or ixx was integral of y square dA. We also saw this parallel axis theorems and then for different shapes. And lastly, in the last part we talked about how do we find the area moment of inertia for some complicated geometries. So in this case of a wide flange beam, we discussed that if we had an additional area, how do we do that? So these are some of the things that we have done, and now let's move to the new concept, what is called as product of inertia. So as I said, inertia is a matrix, and it will have components like, so we will have Ix, and sometimes when I say Ix, it's same as Ixx. Then we will have Ixy, Ixz. Then we will have Iy, which is same as your Iyy, Iyz, and Ixy or Yx. Right. So likewise we will have these components for an inertia matrix. So now let us look at the terms which has got two different terms. So these are called as product of inertia. So when we say moment of inertia, I refer to Ixx, Iyy and Izz. So these are called as moment of inertia, and these terms are called as product of inertia, Ixy, Ixz, Iyz, right? So these are called as product of inertia. So the definition of product of inertia is defined as integral, Ixy is defined as integral of xy dA. So if I have a simple 2D plate, and if I have a small cross-sectional area dA, then the small contribution from this dA is integral of x times y times dA, and then we sum it up for all small particles, and if we have this very small particle and continuum, then we change that summation to an integration. So this is the definition of the product of inertia. Now if we have some symmetric objects, for example, if you see this kind of a cross section, now this is symmetric about x-axis. So if I have this is symmetric about x-axis, and if I write this integral xy dA, so you can see that there is a dA here for which I have a positive y, and then there is another same dA for which I have a negative y, and when I do an integration it will cancel off, and therefore for such symmetric objects the product of inertia is going to be 0. So this is a very important conclusion, a very important understanding, that for symmetric objects this term of product of inertia is going to be 0. The next is, what if I want to change the axis, coordinate axis, right? So same thing for moment of inertia. We have a similar theorem for product of inertia, which is the parallel axis theorem for product of inertia, which again, if you just use this thing, which says that suppose I know I about the center of mass. So the centroid is at point C, and we know I about this thing, which is I bar. So when I say I bar, it refers to the centroid of the area, if I'm talking about area. And if I'm talking about mass moment of inertia, then I bar will refer to I about the center of mass. Now if I want to move my center of, I from measured from point C to point O, then I can write I about the XY axis is equal to I bar about the center of centroid plus X bar Y bar times the area A, the total area A. So that is the parallel axis theorem for the product of inertia. Okay. So with this basic introduction, we at least now know the definitions for moments of inertia Ixx and the product of inertia, and we know some simple theorems to to translate the center of this thing. Now the next thing comes the transformation of this inertia. So when I say now inertia, it should mean to you as inertia matrix. Right. Wait a minute, I hope the recording is going. Yeah. So when I say the inertia, it means inertia matrix, and the coefficients, I mean, if we just talk about a simple 2D case here, so the coefficients of this inertia matrix will be Ix, Iy and Ixy, whose definitions are given as follows in the integral form. Now it may be possible that I want to switch the measurement axis, I want to rotate the axis of rotation. So if I have an object something like this and I have X and Y axis, then we have this I matrix known. Now we want to find the moments and product of inertia with respect to a new axis, let's say X prime, Y prime. So now we have a rotated axis X prime, Y prime, which is rotated by an angle theta, and now we want to find the distribution of area or mass, means the inertia matrix, with respect to the new axis X prime, Y prime. That is the objective. So now again, in interest of time, I am not going through the derivations, I am just summarizing and giving you the final results. So if we want to find the inertia components about the new axis, then here are the results. So these are some complicated looking equations, but these are the equations by which you can get the I about the new transformed axis X prime and Y prime. Right, so Ix prime is equal to Ix plus Iy by 2 plus Ix minus Iy by 2 times cos 2 theta. So if this on the physical geometry, if I rotate the axis by theta, then here it becomes 2 theta. So it is cos 2 theta minus Ixy sin 2 theta. Similarly, Iy prime is given by this expression, and Ix prime Y prime is given by this expression here. Okay. Now we also want to find the directions in which the moment of inertia is maximum and directions in which moments of inertia is minimum, because you know, at least from some basic equations, that the moment of inertia determine your angular acceleration. So if your moment of inertia is high, your angular acceleration is going to be less. If your moment of inertia is low, then your angular accelerations are going to be high, right, for a given amount of moments. So we want to find some directions for which body is easy to rotate. So now we are going to talk about objects which are not symmetrical and three-dimensional objects. So for example, if I show you something like this, I don't know if you can see me. Okay. So if you can see an object something like this, right? So it's a non-symmetrical object. So I want to give you examples for non-symmetrical objects. Or if I have speaker something like this, right? It's a non-symmetrical object, right? So when we have non-symmetrical object, we want to find the direction in which its moment of inertia is maximum and directions in which its moment of inertia is minimum, right? So that is what we are going to try to find. So the maximum moment of inertia, or the direction in which we get maximum moment of inertia, again there are some more mathematics which I am not doing it. The maximum inertia, so it is basically obtained by differentiating it and getting the maximum value. So the maximum moment of inertia is obtained at the following angle, where this theta, when your axes are rotated by angle theta, the tan 2 theta is equal to minus 2 ixy divided by ix minus iy. So by using this expression, we will be able to find the direction in which your your moments of inertia are maximum, and it will also correspond to direction which will have minimum moment of inertia. We will be discussing some examples to make these abstract things more clear, right? So don't worry. The same equations of transformation of inertia or inertia matrix can be expressed in terms of a quantity called as Mohr's circle. So Mohr was one of the engineer who gave a graphical solution, simple solution to represent these complicated equations. So these complicated equations can be expressed in a form of an equation of a circle. So if you modify it a little bit and do the manipulations, we can express these equations as an equation of circle. So the same equation on the previous slide can be expressed as ix prime minus I average. So this is the average moment of inertia, ix plus iy by 2 plus ix prime y prime square is equal to r square. So here I can plot this. So this equation represents equation of circle. R is given by this thing. So I can have a center at x axis with a value of I average. This y coordinate of center of circle is 0 and radius is r, and I can plot this as a circle, right? So this x axis I have ix prime, y axis is ix prime y prime, and then this is a circle with center at I average, right? You can see this is I average and the radius as r. So this is a diagrammatic representation of the same equation on the previous slide, and this circle is called as Mohr circle. And from here we can get what is your maximum and minimum moment of inertia. So point A corresponds to the position where your ix prime is maximum, right? So we want to find the direction x prime for which your ix is maximum, and this point is corresponding to point A, which is your I maximum. Similarly, your point B corresponds to the I minimum position. So this is the point where your ix prime is minimum, and these 2 points A and B are 180 degrees apart. So this angle here represent your 2 theta degree here, right? So this here is 2 theta, and again, so this tan 2 theta, the same expression what we saw in the last slide is here, and your maximum and minimum stresses can be found from this graph. From this diagram you can see the maximum stress will be I average plus radius, and minimum will be I average minus radius. So this is your I average, this is your radius, and your maximum and minimum moment of inertia can be obtained from this equation, and it will happen at a following angular position, right? So now these are equations for ix prime. The same equations can be obtained from iy prime as well, and you will have a similar circle, right? Okay, little bit more definitions, just concluding definitions, and then we will have an example to understand it. So at points A and B on the Mohr circle, we have at point A you can see the ix prime y prime at point A is 0, and similarly for point B, and at A your Ix prime is maximum, but your Ix prime y prime is 0. So therefore the equations for this theta m defines the two angles which are physically they are 90-degree apart. Physically they are 90-degree apart, and they correspond to the principal axis of the area about O. So the configuration of point A and B on the Mohr circle, or the new axis x prime y prime, they correspond to the principal axis principal axis. So what is so special about the principal axis? At principal axis your moment of inertia are maximum and minimum. So your I max and I min are your principal moments, and your product of inertia is 0 at that principal axis, right? So again, I understand there's a lot of definitions and a lot of this thing, and let's see an example, and I hope this will make things very clear to all of you. Here is an example of a uniform and somewhat non-symmetric shape, as you can see here. So it's a 2D cross-sectional area about xy axis. Now here it says that for this section below, the moment of inertia with respect to the x and y axis are given to us. So these are Ix is equal to 10.38 inches power 4. So it's talking about area moment of inertia, and this is about x axis. This value we can calculate, but it is already given to us in the problem, and similarly I about y is given to us, right? And so the whole geometry is given to us, and these are also given. Now the question is, determine the orientation of the principal axis of the section about O. That is first part. And the second part, what are the values of the principal moments of inertia about O? So the question is that if we want to, so as I said in the last class, the area moment of inertia is helpful when we are talking about bending of structures. And if we are talking about mass moment of inertia, then it is about rotation of these structures. So the idea is, now let us say we have an axis x and y. We want to find some axis which may be at some angle, right? We want to find the direction of, let's say, Ix prime, y prime. We want to find what this angle theta should be, such that the moment of inertia about these axes x prime and y prime are maximum and minimum, and obviously along this axis the product of inertia are going to be 0. So we want to find the orientation of the principal axis of this whole section about O, and what are those values. Okay. Okay, so this is the area, and so the first thing which we need to find out is the product of inertia, because product of inertia was not given to us in the problem. So first thing is to compute the product of inertia, and by definition it is summation of x bar y bar times A. Now we can divide this into 3 rectangles, as you can see here. So this is one rectangle, then you have middle rectangle, and then you have the lower rectangle. For the middle rectangle, it is symmetric, so its product of inertia is 0. But for other things, and even for the first rectangle, the product of inertia about this axis is 0 because it is symmetric, but then we have to shift this origin to here, right? So we have to shift its origin from here to point O. So to do this, we use this parallel axis theorem, and and then to compute the product of inertia, we divide this geometry into 3 rectangles and use this parallel axis theorem to get your x bar, y bar, and then x bar, y bar. For the second, it is the coordinates are 0 because it is already at origin, and then we compute this, and using this definition we calculate the product of inertia for this geometry. Now once this is known, we can directly use the formulas that I have given to we have shared. So to determine the orientation of principal axis and the principal moment of inertia, so principal axis direction is given by theta m, 2 theta m is equal to 74.4 degrees and 255 degrees. So these are the values corresponding to the principal axis, and then the I max comma minimum is equal to I average plus minus r. So this is the I average plus minus the radius. So again, just using those equations, we compute the and using Ix and Iy, we compute the I max and I minimum. Right, from these equations, we get this thing. So now let us understand what is the physical interpretation of all these equations and numbers. So as I said that this is the original structure, and let's say we want to rotate or bend this structure about x and y, then we have Ix, Iy and Ixy. But now we want to find a special axis, and which are called as principal axis, which we found, which comes out to be at 75.4 divided by 2, which is 37 degrees here, and 127 degrees here. So so when I rotate the original x-axis to, let's say, axis A, now here about axis A, you can see that the whole structure is very far away from A axis, and therefore its I about A is maximum, which is a very high value, 15.45, right? So out of all these values, you can see I about x is 10 point something, I about y is around 7, but I about A is 15.5. So the moment of inertia is maximum about this A axis, and therefore this is your one of the principal directions. The second is obtained by 90-degree rotation of that direction. So the 90-degree rotation is your axis B, right, which is again obtained by the same equation. 255 divided by 2 is 127 degrees, and you can see about the B axis, the whole structure is very close to B axis, and therefore your I is minimum. So your I is, you can see it's very, very small, 1.8, 1.9. So the elements of the area of the section are more closely distributed about the B axis than about the A axis. Therefore your IA is your I maximum, which is 15.45, and IB is equal to I minimum is equal to 1.89 inches power 4. So these maximum, so A and B are called as principal axis, and the moment of inertia along these principal axes are called as your principal moment of inertia. And again, another point to note is that along these directions A and B, your product of inertia is 0, right? So these are some very important conclusions, and these will be very helpful in the next chapter that we are going to start. So right now what we have done, examples for area moment of inertia, same things are true for the mass moment of inertia. So a very quick definition. So mass moment of inertia is basically your resistance to rotation about an axis AA prime. So if I have an axis AA prime and I want to study the rotation about that axis, then it is integral of r square dm. So that is your definition of your mass moment of inertia. And then we can also define radius of gyration. So if I want to model this rigid body by just a particle at a distance k, then this whole I can be said is equal to mk square, and from there you get your radius of gyration as this expression. So these are same standard things. So I about y axis for a mass is its distance from the y axis, which is square root which is equal to your x square plus z square. So your iy, ix, iz, and your dimensions are kg meter square. Same parallel axis theorems, everything goes in parallel. So if I know I bar about the center of mass, which is g, so I bar about g is known, and I want to find the I about some other axis a prime, which is at a parallel distance of d, then it is, you just add md square, right? And similarly, we have these standard tables for some standard geometries for which mass moment of inertia is tabulated. And then if we have some composite geometry, we can add or subtract these things to get some more complicated geometry. Just a final note on moment of inertia, that if we have moment of inertia about any arbitrary axis in 3D, so if I have for us for a body, if I know I about x, I about y, I about z, and if I want to find it about arbitrary axis lambda vector with components lambda x, lambda y, lambda z, then this is the expression. Again, I'm not going through the derivations, but this is the expression to get the I about any lambda direction. And we can also use this to find your principal axis and principal moment of inertia in a 3D structure, right? Okay, so with that, I'll end this discussion on moment of inertia, and let's start with very interesting and I would say the final topic in this course, which is the kinetics of rigid bodies in three dimensions. So we have seen the kinetics of planar symmetric objects, but now in reality things are all 3D. So this thing has got applications, for example, robotics, space satellites, any 3D object, right? We want to move it, we want to have a complicated motion of 3D structures. The fundamental, let's say if you have a robot and if it has different arms which are moving and rotating, and now we want to compute the moment, the torque and moment that has to be supplied to the motors which control the robotic arm, and those moments have to be computed using the equations that we are going to learn in this chapter, right? So it is essentially a relationship between the motion and forces and moments applied on a 3D structures, but as we will see that equations get quite involved. Okay, so as I said, the three-dimensional analysis are needed for determining the forces and moments on complicated structures. So, for example, this is a very interesting thing that hopefully we will see in the next class, gyroscopes. So gyroscopes and gyroscopic effect are one of the very important findings of this study. Robotic arms, space stations, vehicles, and supports of radio telescopes and so on. So any complicated 3D structures are going to use the motion, or the motion will be described by the equations that we will see in this chapter. Okay. Now the first thing is this Newton's laws remains as it is, so I'm not writing it. So the net force is equal to mass into acceleration of center of mass of that object. So that equation is valid, that is perfectly fine. Let us go to angular momentum. So now the change that will happen is writing the angular momentum and the net moment equation. So rate of change of angular momentum is equal to moment. So when we write that equation for a planar object, that was much simpler equation, and here it is that equation is going to change quite a bit. So let us first of all study how do we express angular momentum for a 3D object. So angular momentum in a fundamental principle is r cross linear momentum, moment of linear momentum. So R cross mv is your basic definition, and again the basic definition of a rigid body is that it is a system of particles put together, right, which is rigidly confined. That's your rigid body. So the basic definition is same. So if I write the angular momentum about the center of mass g, so now here we have a fixed frame O xyz, and then we have another frame which is g small xyz. So right now we are writing angular momentum about the center of mass g, which is r prime cross the linear momentum for that small particle. Ri prime is measured with respect to g, and this is equal. I think there should be a prime here as well. So this should be, I think, vi prime. So this is v vector is your omega cross ri prime. I think let me make that change here, and I'll check it. So I think this should be prime here, which is velocity as observed from g, and this is your omega cross ri prime. Now now if you see this equation, this is a vector equation. So if I write this equation somewhere here, now if I want to evaluate this cross product, so if I just consider the first term, so ri prime has got so it is I cap, j cap, k cap, and then ri will have its component, which will be xi prime, yi prime, zi prime, and then omega cross ri is going to be a vector, but let's write its x component here, let us write its y component here, and let us write its z component here, right? So now what I'm expressing here is this cross product. So it is a cross product of ri vector cross product with this velocity vector here. Ri has component xi prime, yi prime, zi prime, right? So this is the component. Now this is the angular h vector, angular momentum vector. Now it is going to be a little complicated, so let us write the x component of this angular momentum. So just the x component of this angular momentum is going to be, if you see just the I cap component, so it is going to be this multiplied by this minus this multiplied by this, right? So this is going to be this is the h vector, and the hx component is going to be yi times omega cross ri prime minus its z component minus zi times omega cross ri prime's y component, right? So that is the hx. And now if I expand this further, omega cross ri is again, omega is a vector with components omega x, omega y, omega z. Its z component of this cross product is going to be omega x yi minus omega y times xi, right? You can check that. And same way, the y component of this vector is going to be this term here, something like this. Now if we open it up and add it, what we will get is omega x times yi square plus zi square delta m minus omega y xi yi minus omega z zi xi delta m. And this is considering the small particles. If I consider it as a continuum, then this summation will convert into an integral, and what the equation we will get is hx is equal to omega x integral y square plus z square dm minus omega x xy dm minus omega z integral of zm dm. Now we can recognize that this term is your ixx, this term is your ixy, and this term is your ixz, and therefore the hx, the x component of angular momentum, is given by ix omega x minus ixy omega y minus ixz omega z. And these are I bar, so means these are I about the center of mass. And similar way, if we write the y component and the z component, we will get these equations as well. So the angular momentum component in the y direction is given by this, and angular momentum about the z component, the z component of angular momentum is given by this equation. So these are the three equations that we will get, and you can see the difference from the what we have studied in the basic thing. So if we just consider the planar object moving in xy plane, then the omega used to have only the z component, right? If an object is moving in xy plane, if a thin object is moving in xy plane, then omega used to be in the z direction, and what we used to get is only this expression, iz omega z. That was the only term that we used to get, and that used to be equal to the net moment about the z axis. But now, if the object is non-symmetrical, so if it is non-symmetrical, then we will have the product of inertia terms as well. And in three-dimensional, you will have omega x, omega y, omega z. So therefore, the relationship of angular velocity and momentum is going to be a complicated relation expressed something like this. Now this equation, if we we'll use some concepts from linear algebra. So if we use the linear algebra, we can see that what these equations are doing. So these are linear algebraic equations, and this relates a transformation of omega vector into the h vector. H is your angular momentum vector, and this transformation is done by an inertia matrix, which is something like this. So okay, that equation is not here. So I can write the so I can write this as I matrix times omega vector is equal to h vector, or I times omega is equal to h vector. So this equation represents this equation, I times omega is equal to h. And this I matrix is what is called as inertia tensor or inertia matrix, is this matrix plus ix minus ixy minus ixz and so on. So this is the inertia matrix and angular momentum. Now if we choose the if suppose the inertia the directions of if we choose the axis as the principal axis of inertia, which we just now had studied, then for such principal axis we know that the product of inertia terms are 0 for a 3D object. So for a 3D object, if we choose these axes as principal axis, then this matrix becomes quite simplified. And of course, out of these, one term is going to be very large, one term is going to be very small, and one term is going to be in middle of that, right? So that is the typical thing. And if this matrix simplifies to something like this, then this set of equations simplify to the following set of equation: hx prime is equal to ix prime times omega x prime. Hy prime is equal to iy prime omega y prime, and so on. So the angular momentum hg of a rigid body and its angular velocity have the same direction if and only if omega is directed along the principal axis of inertia. So it's a very important conclusion that So for a general body, if it is rotating with an angular velocity omega, its angular momentum can be in a different direction in general, right? So from this equation you can see that the direction of omega vector need not be the direction of h vector. They can be different, but they are only going to be in the same direction if and only if the cross product, this cross terms are 0, and then your omega and h will be in the same in the same direction. So to summarize what we have seen so far, the momentum of or the momenta of particles of a rigid body can be reduced to mass times velocity of the center of mass. When I say V bar stands for center of mass. The angular momentum about the center of mass is related to the angular velocity using this set of equations, something here. And if I want to find the angular momentum about any other point, then we have to add the mv vector as well, r cross mv vector. So if I want to find angular momentum about point O, and if I know angular momentum about point G, then we have to add this r vector, which is the position vector of center of mass, cross the linear momentum of center of mass, or mv bar. And now if I consider the rotation about a fixed point, so this is again a special case that if we consider, if this body is rotating about a fixed point O, and one common example is a top rotating, right? So if I have a top which is rotating about a point O, that's a typical example of that. So if the body is constrained to rotate about a fixed point O, then again we can write this equation, and we can also calculate the angular momentum by the moment and product of inertia with respect to the frame OXYZ. So I can even directly from the fundamental principle, I can calculate R cross MV with respect to this point O, right? So if this body is rotating about point O is fixed, then I can say R cross MV is your angular momentum, and this is this expression here. And again, if I simplify this expression, this Ix will be I about x-axis, Ixy is product of inertia about xy axis, Iy is moment of inertia about y-axis, and so on. So I can again write a similar expression, something like this. Now, if we just write the principle of impulse and momentum, so right now we have seen momentum, and if I just want to write the principle of impulse and momentum. So what it says that in configuration 1 or configuration A, the system has got a linear momentum mv and it has got an angular momentum hg1. Then from T1 to T2, or from configuration A to configuration C, there is some intermediate impulses that are acting on it, integral of f dt. And due to this impulse, the momentum changes, and now the new momentum is mv2 and hg2. So what it says that the momenta at first configuration plus impulse is equal to the momenta at second configuration. So same thing can be written for linear case as well as for the rotational case as well. So these equations can be written, and these are some examples which hopefully we will see in the coming classes. Or these are some examples of fixed point rotation. So for example, this top is rotating about O, and this object is rotating about this axis, and it has also another rotation. So far in this class we have seen about angular momentum. We have derived a relationship of angular momentum and angular velocities, and we have seen the transformation is related by an inertia matrix. In the next class we are going to differentiate this expression, and get the expression of rate of change of angular momentum to the external moments applied, right? So I think that's all for this discussion.